In the linked video, we have already explained the necessity of specifying tolerances in detail. These tolerances referred exclusively to dimensional specifications, so that in this context they are also called dimensional tolerances. Dimensional tolerances generally describe the permissible deviations of a dimension. Their purpose is to ensure the function of components. For example, if a rolling bearing is to be mounted on a shaft using a clearance fit, the tolerance of the shaft must be chosen so that the outer diameter of the shaft is always smaller than the inner diameter of the bearing. However, simply specifying a dimensional tolerance does not necessarily guarantee that the shaft will actually fit into the bore of the rolling bearing. The shaft can, for example, deviate from the ideal cylindrical form and be curved to a greater or lesser extent. This curvature of the shaft then prevents the shaft from fitting into the rolling bearing, despite compliance with the dimensional tolerance. This deviation from the ideal form is not in contradiction to the dimensional tolerance. If the diameter of the shaft were measured at different points, it would still lie within the dimensional tolerance despite the curved form. The dimensional tolerance could, in principle, be chosen as small as desired, but it could not prevent the shaft from being overall curved. For this purpose, the shaft can be imagined as being cut into many small discs, each of which lies within even the smallest dimensional tolerance. In the case of a curved shaft, the discs no longer lie on a straight axis, but on a curved one. This example therefore makes it clear that it is generally not sufficient to specify tolerances only for dimensions, but that tolerances for form deviations must also be specified. In our case, it would therefore be sensible to specify a maximum permissible deviation from the cylindrical form. The specification of such a deviation of cylindricity will be explained in more detail later. As was already made clear by the example just shown, the geometry of a component usually must be toleranced in addition to the dimensions. Such geometric dimensioning and tolerancing, also called GD&T, can be divided into form and positional tolerances, where the positional tolerances can be further subdivided into orientation, location, and runout tolerances. In this video, we will focus first on the form tolerances. We will cover the positional tolerances in more detail in a separate video. The geometric forms to be toleranced include straightness, flatness, roundness, cylindricity, arbitrarily curved profile line form as well as profile surface form. Let us first take a closer look at the tolerancing of straightness. For this purpose, we consider the illustrated example of a triangular prism with a width of 50 mm and a height of 25 mm. The upper edge of the prism is intended to function as a kind of ceiling lip and therefore should be as straight as possible. Although the height is very finely toleranced at plus or minus 0.1 mm, this does not automatically mean that the upper edge is also as straight as possible. The actual geometry could also look like the illustration, and despite this, a 2-point measurement with a caliper along the entire length of the prism would still show a height within the tolerance. Even here, no matter how small the dimensional tolerance, it cannot prevent the prism from being curved. The tolerancing of a geometric feature, in this case the tolerancing of an as straight as possible edge, is carried out like all geometries to be toleranced using a so-called feature control frame, also known as a tolerance indicator. This rectangular frame first points with an arrow to the geometric feature to be toleranced, in this case our prism's upper edge. In the first box of the feature control frame, the symbol representing the geometric feature to be toleranced is placed. A horizontal line here indicates the feature of straightness. After that, the width of the tolerance zone is specified in millimeters, in our case 0.04 millimeters. We will shortly see how to interpret this specification. Let us consider the prism in the sectional view for this purpose. In addition to the dimensional tolerance, a further tolerance zone is now established by the form tolerance, which in our case defines the straightness. This is represented by two parallel lines spaced 0.04 millimeters apart. The actual geometric feature, in this case our prism's upper edge, must lie within this red-marked zone. The shown course of the upper edge would, in this case, be within the form tolerance zone at every point and thus acceptable. The width of the tolerance zone of 0.04 millimeters essentially specifies the maximum waviness that must not be exceeded, so that the geometric feature is then considered straight. Note that the only restriction for straightness is that the actual geometric feature must lie within the two parallel lines. The position of the parallel lines does not matter. Therefore, the form tolerance zone may also be inclined. As long as the geometric feature lies between the two imaginary parallel lines, the straightness according to the form tolerance is fulfilled. Straightness thus imposes no restriction regarding the position of the geometry. That is why straightness is not classified as a positional tolerance but as a form tolerance, which only makes a statement about the form and not about the precise position. In contrast to positional tolerances, form tolerances do not require a reference to another feature to determine their position. To establish parallelism to another geometric feature, such as ensuring the upper edge is parallel to the lower edge of the prism, positional tolerances are required, which will be explained in more detail in a separate video. Instead of the prism, let us now consider a cuboid-shaped component. In this case, the top surface is not a one-dimensional edge but a two-dimensional surface. This top surface is intended to serve as a support surface for another component and therefore must be as flat as possible. This generally applies to all ceiling surfaces. For this reason, we initially also tolerate the top surface with straightness. However, we will soon see that this is not effective in this case. Let us also consider the cuboid in the sectional view. Since the feature of straightness is now applied to a surface, the actual edge of the component must lie between two parallel lines spaced 0.04 mm apart in every sectional plane parallel to the drawing plane. We mentally pass through our component perpendicularly to the back and check whether the corresponding straightness of the surface edge is maintained for each sectional plane. As the animation shows, this is the case. Every inspected surface line can thus be considered straight, and the component is deemed acceptable. As we can see from the side view, however, this does not mean that the surface itself is flat. The surface is only straight parallel to the tolerated edge, but not necessarily perpendicular to it. To ensure a certain flatness, we would therefore also need to restrict the straightness in the perpendicular direction. What we ultimately obtain from this are two parallel planes spaced 0.04 mm apart, within which the waviness of the entire surface must lie. To avoid having to tolerate two straightnesses perpendicular to each other for every surface, there is the flatness symbol in the form of a parallelogram. If we mentally pass through our component again, the surface must lie within two parallel planes spaced 0.04 mm apart. Note again at this point that, similar to straightness, the position of the parallel planes does not matter for flatness. The planes may therefore be inclined, as long as they are parallel to each other. As long as the tolerance geometric feature, in this case the component surface, lies between the two imaginary parallel planes, flatness according to the form tolerance is fulfilled. Flatness thus imposes no restriction regarding the position of the surface. To achieve parallelism of the surface to the bottom side, positional tolerances are again required, which will be covered in another video. Let us briefly return to the geometric feature of straightness at this point. Consider the shaft shown at the beginning, whose axis should be as straight as possible and not curved. Such a curvature of the centerline can also be restricted using the geometric feature of straightness. We must not place the leader arrowhead on the surface of the shaft. If we did, we would only be tolerating the straightness of the surface line. Here, however, we want to tolerate the straightness of the shaft axis and thus of the centerline. Therefore, in this case, the leader arrowhead is placed in direct extension of the diameter dimension line. This means that the straightness tolerance now refers to the geometric feature derived from the diameter, in our case the centerline. We will discuss the terms actual and derived geometric feature in more detail later. According to the definition of straightness, the shaft axis must now lie between two parallel lines spaced 0.04 mm apart. Strictly speaking, in this case, we would only be restricting the curvature of the shaft axis within the illustrated cross-sectional plane. However, the position of this cross-sectional plane relative to the part would not be clearly defined, since the shaft is rotationally symmetrical. If, for example, a keyway were present, the position of the shaft and thus the cross-sectional plane would be clearly defined. In that case, the keyway would be viewed directly from above. Thus, we would only be restricting the straightness of the shaft axis in the plane, where we are also looking directly at the keyway from above. Perpendicular to this plane, the shaft may still be curved arbitrarily. Theoretically, we could now restrict the waviness of the axis in the shown plane with an additional straightness tolerance. This is similar to how we previously restricted the flatness of a surface using two straightness tolerances perpendicular to each other. However, this type of straightness tolerance is not very useful for rotationally symmetrical parts, because it results in a rectangular tolerance zone along the axis. That means the tolerance would be larger in the diagonal direction than along the edges of the tolerance zone. A much more meaningful approach here is a cylindrical tolerance zone, which is also rotationally symmetric according to the shape of the part. We no longer talk about two parallel lines at a distance of 0.04 mm, but rather about a tolerance cylinder with a diameter of 0.04 millimeters, within which the shaft axis must lie. If this condition is met, the shaft axis is considered straight in terms of the form tolerance. It should also be noted here that the position of the tolerance cylinder is not specified. The only requirement for straightness is that the shaft axis must lie within the form cylinder, but the tolerance cylinder itself does not have to be aligned with the cylinder. In particular, the tolerance cylinder does not need to run exactly coaxial to the centerline of the ideal shaft. It can also be offset or slightly inclined relative to the centerline. The only condition is that the actual shaft axis must lie within the arbitrarily positioned tolerance cylinder. However, to indicate in the drawing that straightness is no longer controlled by two parallel lines, but instead described by a cylinder with a specified diameter, the diameter symbol must be placed before the tolerance value in the feature control frame. So note, when tolerancing the straightness of a centerline, the leader arrowhead is drawn in the extension of the dimension line. If the tolerance zone for rotationally symmetric geometries is to be cylindrical, a diameter symbol must precede the form tolerance value. The centerline must then lie within a cylinder whose diameter corresponds to the specified tolerance value. One might assume that specifying a perfectly straight axis and a diameter tolerance would automatically ensure a certain roundness of the shaft. At first glance, this seems logical, since it might appear that with a perfectly straight axis and an exactly specified diameter, an ideally round cross-section would naturally result. So if we limit the maximum waviness of the axis by specifying the straightness tolerance and restrict the deviation from the nominal diameter with a dimensional tolerance, a certain roundness should automatically be achieved. But this is a misconception. Even if the axis is perfectly straight and the shaft's diameter of 25 millimeters is exactly maintained, this does not automatically mean that the shaft is actually round. Let's look at the cross-section of the shaft shown here, which is clearly far from perfectly round. Yet, using a two-point measurement with a caliper at any position around the shaft would yield exactly the nominal dimension. This means we could meet the nominal size along the entire length of the perfectly straight axis, and still, the shaft would obviously not be round. Note that we previously saw that a shaft can be perfectly round while its axis runs in a wavy, snake-like path. Now we see that the opposite is also true. A perfectly straight axis does not necessarily mean the shaft itself is round. Straightness and roundness are therefore completely independent of each other and must be considered and, if necessary, toleranced separately. Roundness is defined by two concentric circles, which form an annular zone within which the actual geometric element must lie. The roundness symbol is a circle, and the specified tolerance value corresponds to the distance between the concentric circles, or, in other words, the thickness of the tolerance ring. It is important to note, however, that neither the position of the tolerance ring nor its diameter is defined by the roundness. In particular, this means that the center of the concentric circles does not necessarily have to lie on the shaft axis. The diameter of the rings also does not have to remain constant, but can increase or decrease along the imagined path along the shaft axis. The only condition for roundness is that the actual geometric element lies within the tolerance ring, but the position and diameter of the ring itself are not fixed. In our case, the width of the tolerance ring is 0.03 millimeters. If the actual geometry lies entirely within this annular tolerance zone, the shaft is considered round. To specify the roundness tolerance, the form tolerance arrow is placed on the corresponding surface. The roundness then applies to every imagined cross-section along the relevant axis. In the illustrated case, the roundness applies along the entire length of the shaft. If the shaft tapers in the middle section and the tolerance arrow is placed, as shown, only on the concave line geometry, then the roundness applies solely to this concave geometric feature. No specific roundness is required for the cylindrical shaft ends. Note that the roundness tolerance zone does not limit the diameter of the shaft, but only the width of the annular tolerance zone, which in our case is 0.03 millimeters. Therefore, applying a roundness tolerance is especially useful for parts whose diameter, as in our example, is not constant, but whose individual cross-sections still need to maintain a certain roundness. For parts with a constant diameter, such as shafts that should be as cylindrical as possible, using roundness tolerance is generally not effective. For example, if the surface of the depicted shaft were tolerated using roundness, it would not necessarily result in a cylindrical shape, since the roundness tolerance zone does not limit the diameter. For cylindrical parts, the deviation from the cylindrical form is limited by defining the tolerance zone not by two concentric circles, but by two coaxial cylinders, which together form a hollow cylinder. This sets the same inner and outer diameter as form tolerance limits for every cross-section. The actual geometry must lie within these two coaxial cylinders. The symbol for cylindricity in the feature control frame is represented by a circle bounded by two parallel lines. The tolerance value indicates the distance between the two tolerance cylinders. This corresponds to the thickness of the hollow cylinder within which, in our case, the surface of the shaft must lie. Again, the axis of the hollow cylinder does not necessarily have to coincide with the ideal centerline of the part, nor does it have to be parallel to it. Similarly, the diameters of the two coaxial tolerance cylinders are not specified, only their distance, which in our case is 0.03 millimeters. As can be seen from the two-dimensional drawing, cylindricity not only limits the deviation of the geometry from the ideal cylindrical form, but also the straightness of the cylindrical surface. Essentially, in the shown two-dimensional representation, we are dealing with two parallel lines within which the generatrix of the shaft surface must lie. This corresponds exactly to the definition of straightness. The same applies to axiality, which means the straightness of the shaft axis. This is also indirectly controlled by the cylindricity tolerance. In the end, the shaft axis cannot be curved arbitrarily, because otherwise the surface would no longer lie within the coaxial tolerance cylinders. Therefore, for example, it does not make sense to specify a straightness tolerance for the shaft axis if a smaller cylindricity tolerance is already applied, as shown here. The deviation of the shaft axis from the ideal straight line can be at most as large as the allowed cylindricity tolerance. So note, cylindricity includes roundness, axiality, and the straightness of a generatrix. So far, the consideration of geometric elements has essentially been limited to two basic geometric shapes, the straight line and the circle. However, components can also have more complex geometries that can no longer be described by these simple basic shapes. The illustrated example shows a thin sheet metal part whose upper edge cannot be described by either circular or straight segments. Even such complex line profiles must be toleranced in form to ensure that they do not deviate too much from the ideal shape of the CAD model during manufacturing. For this purpose, the so-called line profile tolerance is used. The symbol for this profile tolerance is an open semicircle. With such complex line profiles, it is often not obvious between which points this geometric feature exactly lies. That is where the geometric feature begins and where it ends. For example, the profile tolerance might refer to the entire upper line profile or only a part of it. To precisely indicate which section of the line belongs to the tolerance geometric feature, it is therefore marked with two arrows and corresponding letters. Since there can be multiple line profile tolerances in a drawing, the corresponding letters are indicated above the tolerance frame separated by a double arrow. The tolerance zone can be imagined as an infinite number of circles whose diameters correspond to the form tolerance value and whose centers lie on the ideal geometry. The overlay of these circles then forms the form tolerance zone. However, the ends of the tolerance zone are not rounded but oriented perpendicular to the line profile. The actual geometry of the sheet metal edge must lie within the resulting tolerance zone. However, the tolerance zone itself does not have to be exactly aligned with the ideal geometry. It can be positioned arbitrarily relative to it. For example, we can rotate the tolerance zone or shift it up and down, or left and right. The only condition is that the actual geometric feature must lie within the tolerance zone, regardless of how the tolerance zone is precisely oriented. The ideal geometry is used solely to determine the shape of the tolerance zone, but not its position. The line profile tolerance can basically also be applied to a straight line. When the circles overlap, they create an envelope defined by two parallel lines spaced according to the tolerance value, within which the actual geometric feature must be contained. This ultimately corresponds to the definition of straightness. Thus, the line profile tolerance can also be used to tolerate straightness. The same principle applies to roundness. When applying the line profile tolerance to a circle, the overlapping of infinitely many tolerance circles creates an annular tolerance zone, bounded by two concentric circles whose distance corresponds to the tolerance value. In this way, roundness can also be tolerated using the line profile tolerance. So note, the line profile tolerance can be used not only to control the shape of arbitrarily curved geometric features, but also, in particular, to specify straightness and roundness tolerances. Instead of the thin sheet metal, a thicker component with corresponding depth is now considered. Compliance with the tolerance zone must then be ensured in every cross-sectional plane parallel to the surface. To do this, we can mentally move through the tolerance zone perpendicular to the surface. It must then be checked whether the actual line profile of the surface lies within the tolerance zone. This is only possible if the nominal line profile remains constant, meaning the front side of the component is simply extruded backward. In this case, the surface changes only along the line profile, but not perpendicular to it. The cross-sectional planes perpendicular to the surface then form straight lines. However, let us now consider a component whose surface is curved in arbitrary directions. For such surfaces, in addition to the profile tolerance for arbitrarily shaped lines just explained, there is also a profile tolerance for arbitrarily shaped surfaces. In the feature control frame, the open semicircle is then shown as a closed one. The tolerance zone is obtained by imagining infinitely many spheres with a diameter equal to the form tolerance value, whose centers are distributed over the tolerated surface. The envelope of these spheres on the upper and lower sides corresponds to the form tolerance zone. The actual surface must then lie between these equidistant boundaries. The surface profile tolerance can basically also be applied to a plane. When overlapping the spheres, two parallel planes result, whose distance corresponds to the tolerance value, and within which the actual geometric element must lie. This ultimately corresponds to the definition of flatness. Thus, flatness can also be tolerated using the surface profile tolerance. Similarly, this applies to cylindricity. If we apply the surface profile tolerance to a cylindrical surface, the overlapping of infinitely many tolerance spheres results in a hollow cylinder bounded by two coaxial cylinders, whose distance from each other corresponds to the tolerance value. In this way, cylindricity can also be tolerated using the surface profile tolerance. So note, surface profile tolerance can be used not only to tolerate arbitrarily curved surfaces in their shape, but specifically also flatness and cylindricity. We have now become familiar with the 6 form tolerances and their characteristics. Let's briefly summarize them once again. For straightness, the actual geometric feature must lie between two parallel lines whose distance corresponds to the form tolerance value. In this case, the tolerance zone is rectangular. When straightness is applied to a real geometric feature, such as an edge or a line on a surface, the leader arrowhead must point to the edge, the surface, or the corresponding extension line, but it must be placed at least 4 mm away from the dimension line. If straightness is applied to a derived geometric feature, such as a centerline, the leader arrowhead is placed in extension of the dimension line. A diameter symbol before the tolerance value indicates that the form tolerance zone is cylindrical, and the centerline must lie within a cylinder whose diameter corresponds to the form tolerance value. In this case, the tolerance zone is cylindrical. For flatness, the tolerated surface must lie between two parallel planes whose distance corresponds to the form tolerance value. The tolerance zone is cuboid-shaped in this case. For roundness, the tolerated geometric feature must lie between two concentric circles, whose diameters can in principle be chosen arbitrarily, but whose distance must correspond to the form tolerance value. In this case, the tolerance zone is ring-shaped. For cylindricity, the tolerated geometric feature must lie between two coaxial cylinders. The diameters of these cylinders can be chosen arbitrarily, but their distance must correspond to the form tolerance value. The tolerance zone in this case is a hollow cylinder. The line profile tolerance is a generalization of straightness and roundness. The arbitrarily curved profile line must lie between the envelope lines of infinitely many circles whose diameters correspond to the form tolerance value, and whose centers lie exactly on the ideal geometric profile line. In each parallel cross-section, this profile shape must be independently maintained. The surface profile tolerance is a generalization of flatness and cylindricity. The arbitrarily curved profile surface must lie between the envelope surfaces of infinitely many spheres whose diameters correspond to the form tolerance value, and whose centers lie exactly on the ideal geometric profile surface. Now that we have covered the various form tolerances, we will take a closer look at several auxiliary indicators. These are used alongside the feature control frame to provide further information. Let's once again consider the example of a rectangular block whose top surface is toleranced for straightness as shown. It was already explained that when straightness is applied to a surface, the requirement must be met in every cross-sectional plane parallel to the drawing plane. It should be noted that in some cases it can make perfect sense to specify straightness on a surface instead of flatness. This is because straightness is inherently one-dimensional, whereas flatness applies to a two-dimensional area. As a result, the manufacturing and inspection effort for flatness is higher, since straightness effectively needs to be satisfied in two perpendicular directions. Therefore, if the parts function allows it, specifying straightness instead of flatness on surfaces can be a practical choice. This means that straightness only needs to be maintained in one direction. Perpendicular to that, the surface can theoretically have any waviness, as is the case in our example. But the question arises, who determines the direction in which straightness must be maintained, and in which it may be wavy? Here, we have implicitly assumed that straightness is required in a cross-sectional plane parallel to the drawing plane. However, the conceptual cross-sectional plane used to define straightness could also be oriented at a different angle relative to the drawing plane. Without additional specification, the supplier could essentially choose any direction for the straightness requirement. Therefore, it is both useful and necessary to define the orientation of the cross-sectional plane in which straightness must be maintained. This is done using a so-called section plane indicator. This indicator is usually placed to the right of the feature control frame and consists of two boxes. The first box specifies the orientation of the section plane relative to the reference surface indicated in the second box. The actual symbol of the section plane indicator is a triangle that connects the indicator to the feature control frame. The reference itself must then be indicated in the drawing. It consists of a filled datum triangle and a datum frame above it, connected by a short line. The datum letter is entered in the datum frame. In our example, the reference is set on the part surface in the drawing plane and labeled A. In the first box of the section plane indicator, the parallelism symbol can then be entered, for example. This makes it clearly defined in which section plane straightness must be fulfilled, in all section planes that are parallel to the specified datum surface A, which corresponds to the drawing plane. Alternatively, the side surface could be chosen as datum surface B, and the section plane specified as perpendicular to this datum surface. If straightness is also to be controlled in the direction parallel to datum B, two feature control frames can be arranged directly below one another. These frames should be ordered so that the tolerance values decrease from top to bottom, meaning the tolerances become tighter. In this case, the waviness in section planes parallel to datum surface B must not exceed 0.08 mm, and in the perpendicular direction it must not exceed 0.04 mm. For better clarity in technical drawings, the datum can also be combined directly with a feature control frame. In our example, the right side is specified with a flatness tolerance of 0.04 mm. This side surface simultaneously serves as datum B, which allows the datum triangle to be attached directly to the feature control frame. The section plane indicator is not only used for straight geometry elements, but also for arbitrarily shaped geometries, such as line profiles. It is always required when a tolerance line is located on a surface, or when it is not clearly identifiable whether a line or a surface is being toleranced. However, the section plane indicator is not used for generatrices on cylindrical surfaces, or for roundness on spherical, conical, or cylindrical parts. Another auxiliary indicator is the so-called direction element indicator. This indicator is used whenever it is not clear whether the tolerance zone is perpendicular to the tolerated surface. While in the case of roundness tolerancing on cylindrical surfaces the tolerance zone is, by default, always oriented perpendicular to the surface, this is not necessarily true for conical surfaces. Let's consider the example of the conical surface shown, which is specified with a roundness tolerance of 0.05 mm. We will examine this part in section view. Basically, for non-cylindrical surfaces, there are two possible ways the tolerance zone can be oriented. In the case shown, it lies directly in the section plane and is therefore perpendicular to the centerline, that is, perpendicular to the part's axis. However, this does not necessarily have to be the case, since the tolerance zone can also be oriented perpendicular to the part surface, meaning perpendicular to the conical generatrix. In this case, the ring-shaped tolerance zone forms a conical surface, with a distance between the concentric circles defining the conical surface still corresponding to the specified tolerance value of 0.05 mm in our example. This distinction whether roundness is tolerated perpendicular to the axis or perpendicular to the surface must also be considered when measuring roundness with a dial gauge. If roundness is tolerated perpendicular to the surface, the dial gauge must be positioned perpendicular to the surface as well. For a roundness tolerance of, for example, 0.05 mm, the dial gauge's needle may then deviate by a maximum of 0.05 mm. If the roundness is tolerated perpendicular to the axis, then the dial gauge must also be aligned perpendicular to the axis, and the maximum needle deviation in this plane must be observed. The deviations measured perpendicular to the axis are generally different from those measured perpendicular to the surface. Therefore, when tolerancing roundness of non-cylindrical surfaces, it is necessary to specify whether the roundness refers to the direction perpendicular to the axis or perpendicular to the surface. This is where the direction element indicator is applied. In our case, we want to tolerate the roundness perpendicular to the part axis. Therefore, we first need to specify the centerline of our cone as the datum. To do this, we place datum A directly in line with the dimension line for the cone's included angle, which in our case is 20 degrees, so that the datum does not refer to the cone surface, but to the geometry element derived from it, that is the centerline. The actual symbol for the direction element indicator is an arrow pointing to the feature control frame. In the first box, the characteristic is specified, in our case the perpendicularity symbol, and in the second box, the datum is indicated. This clearly defines that the roundness is to be tolerated perpendicular to the centerline and must be inspected accordingly. If, on the other hand, the roundness is to be tolerated perpendicular to the conical surface, a runout symbol with an arrow is used instead of the perpendicularity symbol. In this case, the roundness must also be inspected perpendicular to the surface. In addition to the section plane indicator and the direction element indicator, there are also an orientation plane indicator and a collection plane indicator. The orientation plane indicator is similarly structured to the section plane indicator, but has an unfilled triangle on both sides, to the right and left of the two boxes. This indicator is mainly relevant for position tolerances, which we will discuss in more detail in another video, where we will also cover this orientation plane indicator more thoroughly. For the sake of completeness, we mentioned this indicator here already. The last of the four auxiliary indicators is the collection plane indicator, which we will discuss in more detail later in this video. It is symbolized by a circle that connects the auxiliary indicator with the feature control frame in the drawing. To understand the function of this collection plane indicator, we will first take a closer look at various modifiers in the following. Let's consider the shown example of a part with a groove cut into its top surface. The surfaces on the left and right sides of the groove are intended to serve as a common mounting surface for another part and therefore need to be as flat as possible. We thus specify flatness tolerances of, for example, 0.05 mm for both surfaces. Since this tolerance is meant to apply equally to both surfaces, instead of using two separate feature control frames, we can use a single frame with two arrows pointing to the respective geometries. It is important to note, however, that tolerated geometric elements always form independent tolerance zones, even if both geometries share a common feature control frame. In this case, each tolerated geometric element, that is the two surfaces to the left and right of the groove, is checked independently for flatness. There is no shared tolerance zone. Rather, the tolerance zones for both elements can be positioned arbitrarily relative to each other. Let's consider the depicted real surface and schematically draw the tolerance zones for both surfaces. As can be seen, both surfaces lie within two independent tolerance zones, each 0.05 mm wide. Thus, flatness is fulfilled for both surfaces and the part is considered acceptable. However, such a tolerance specification is not practical in this case because the two surfaces serve as a common contact surface. It would therefore be more sensible for both surfaces to share a common tolerance zone. As we can see, in this case the flatness of the two combined tolerance zones would not be met. To clearly indicate that the two tolerated geometries should form a combined tolerance zone, the so-called combined zone modifier CZ is specified in the feature control frame after the tolerance value. So note, by default, each tolerated geometric feature receives its own independent tolerance zone, unless the CZ modifier is specified. However, to explicitly indicate in some cases that separate independent tolerance zones are intended, the separate zone modifier SZ is used. Let's look at another example demonstrating the use of an important modifier. The goal is for the right side of the part, between points J and K, to closely match the intended shape. The part contour includes, among other features, two quarter circles. Therefore, we select the surface profile as the form tolerance. Here it is again important to note that by default, each geometric element is assigned its own tolerance zone. In our case, we are dealing with a total of 5 geometric elements which should ideally be clearly indicated in the drawing through corresponding dimensions. For simplicity, this was omitted. The different geometric elements are shown in the drawing in different colors. They consist of 3 straight lines, 2 horizontal surfaces and 1 vertical surface, as well as 2 quarter circles or 2 cylindrical mantle surfaces. Each geometric element now has its own independent tolerance zone. These tolerance zones are formed, as usual with surface profile tolerances, by the envelope of imaginary spheres whose centers lie on the respective ideal geometry. However, as already explained, the ends of the respective tolerance zones are not rounded but flat. This will be important later on. The respective tolerance zones are schematically shown in different colors in the drawing and must be inspected independently of each other. However, the individual tolerance zones can also be shaped as shown, with each geometric element still lying within its tolerance zone. Thus, the part is considered acceptable even though the overall shape obviously looks quite different from what we originally expected. Therefore, at this point as well, we must clearly indicate with the CZ modifier placed after the form tolerance value that the tolerance zones of the geometric elements are not to be considered independently, but combined. There is also another way to define such a combined tolerance zone at this point. While the CZ modifier first establishes tolerance zones for the individual geometric elements and then combines them, there is another modifier that treats the geometric elements as a single entity, forming the tolerance zone directly from this combined geometry. This is the so-called United Feature Modifier UF. However, this modifier is not placed after the tolerance value, but positioned above the feature control frame. In this case, the 5 geometric elements are no longer considered separately but treated as a single entity. The tolerance zone is again formed as the envelope of imaginary spheres. The actual geometry must lie within this tolerance zone. Upon closer examination, we can now see the difference from the CZ modifier. With the UF modifier, the outer transition of the tolerance zone from the horizontal to the vertical surface is rounded, not sharp as it is with the CZ modifier. So note, with the UF modifier, the individual geometry elements are considered as a single element, from which the tolerance zone is formed. This leads to a smoother transition of the tolerance zone at abrupt geometry changes. A small additional note, unlike the CZ modifier, the UF modifier can be used not only for form tolerances but also for dimensional specifications. Therefore, the UF modifier is not placed directly after the form tolerance value, but positioned more generally above the feature control frame. The modifiers also differ in how the part's form is inspected. When using the CZ modifier for a combined tolerance zone, the form of each individual tolerance zone must still be checked separately and documented accordingly. In contrast, when using the UF modifier as a united geometry element, the entire tolerance zone is inspected as a whole and documented only once. Let's return to our part. In the current example, we have only tolerated the shape of the part between points J and K with respect to the surface profile. However, if we want to tolerate the entire circumferential shape of the part, we can mark the bend of the leader line with a circle. This means that the surface profile tolerance now applies all around the entire part shape. Combined with the UF modifier, this results in the depicted form tolerance zone for our part. If the all-around symbol is used, it is always necessary to specify exactly what is meant by all-around. Without further indication, this leaves room for interpretation. Here we have assumed that the outer contour of the part is described in a plane parallel to the drawing plane. However, it would also be possible to describe the outer contour in another inclined plane around the part. This plane, in which the different geometry elements are effectively collected when using the all-around symbol, is called the collection plane. To define the position of this collection plane, the previously mentioned collection plane indicator is used. Like the all-around symbol, it is marked with a circle that connects the auxiliary indicator to the feature control frame. In the first box, the orientation is specified again, and in the second box the corresponding datum. In our case, this means that the form tolerance applies to a series of geometric features describing the circumference of the workpiece when viewed in a plane parallel to datum surface A. According to the standard, the use of the collection plane indicator is mandatory whenever the all-around symbol is applied. Let us conclude with a brief look at the frequently used terms real geometric feature and derived geometric feature. As already explained, a form tolerance always refers to a derived geometric feature when the leader arrowhead is placed directly in line with a dimension line. In the case of a diameter dimension, this means that the tolerance does not apply to the surface of the part, but rather to the centerline. In principle, the following applies. Derived features are geometries that cannot be measured directly, but can only be determined indirectly. These include the already mentioned centerlines of rotationally symmetric parts, such as shafts. The centerline cannot be measured directly. Instead, its course can only be determined by measuring the diameter or cross-section at many different positions and then calculating the centroid through which the centerline must pass. It is therefore only possible to draw indirect conclusions about the course of the centerline. The path of the centerline is essentially derived from real measurable geometries. That is why a centerline is considered a derived feature. The real measurable geometry is accordingly referred to as an integral feature or feature of size. The same applies to the median planes of symmetrical parts. Such a median plane cannot be measured directly either. Its position can only be determined indirectly by measuring real geometries. Therefore, a median plane is also considered a derived feature. Another derived geometry feature is the center point of a bore. This point is also not directly measurable but can only be determined by measuring a real geometry feature, such as the internal diameter of the bore, from which the position of the center point can then be derived. Bolt circle diameters are also considered derived geometry elements because they describe the arrangement of bore center points on a circle and therefore cannot be measured directly. Similarly, the pitch circle diameter of a gear is a derived geometry since it cannot be directly measured. It is no coincidence that all these derived geometry elements are always represented as thin chain lines in technical drawings. This is prescribed by the standard. So note, integral geometry elements or features of size can be measured directly and are depicted in technical drawings by thick continuous lines, for example edges of parts. Derived geometry elements, on the other hand, cannot be measured directly and are shown in technical drawings as thin chain lines, for example centerlines, center points, median planes, or pitch circles.